Software and programming. Software and programming are at the heart of modern technology, serving as the creative and logical forces that drive everything from simple mobile applications to complex distributed systems powering global enterprises. At its core, software is the set of instructions that tells hardware what to do, while programming is the art and science of writing those instructions in a way that machines can execute efficiently and accurately. This discipline has evolved dramatically over the decades, transforming from the early days of punch cards and assembly language into a sophisticated ecosystem that embraces high-level programming languages, object-oriented design, functional paradigms, and modern development methodologies. The transformation has not only increased efficiency but also democratized access to technology, enabling individuals and organizations alike to solve complex problems and address real-world challenges in innovative ways. The process of creating software begins with careful problem analysis and planning. Developers start by understanding the requirements of the task at hand, which can range from automating routine office work to running intensive simulations in scientific research. This initial phase involves the conceptualization of the system architecture, where decisions are made about which components are necessary and how they will interact. In many cases, this planning stage includes designing data structures, selecting appropriate algorithms, and outlining the overall flow of the program. By establishing clear objectives and a solid design, programmers set a firm foundation for the implementation phase where detailed coding takes place. This disciplined approach ensures that the final product is not only efficient but also scalable and maintainable, essential qualities in an era where software is expected to evolve continually alongside emerging user needs and technological advancements. An essential facet of programming is the choice of programming language, which is influenced by the nature of the problem, performance requirements, and developer proficiency. Languages such as Python, Java, C++, and JavaScript have become ubiquitous due to their distinct features and extensive libraries that make them suitable for a wide range of applications. Python, for instance, is celebrated for its readability and simplicity, making it a favorite for rapid prototyping, data analysis, and machine learning. In contrast, C++ is often preferred when performance and low-level system manipulation are critical, as seen in games and high-frequency trading systems. Regardless of the language chosen, the underlying principles of algorithm design and data structure utilization remain constant, providing a framework that guides developers in creating efficient, reliable code. This focus on core computational concepts ensures that programmers can adapt to new languages and paradigms as technology continues to evolve. Central to the practice of programming is the design and implementation of algorithms, which are step-by-step procedures that solve specific problems or perform computations. Algorithms can be as simple as sorting a list of numbers or as complex as managing large-scale artificial intelligence systems. Their efficient implementation is crucial since even slight improvements can lead to significant enhancements in performance, especially when dealing with vast quantities of data or high-frequency operations. Developers invest considerable time in understanding computational complexity and choosing the right algorithmic approach to ensure that their software not only works correctly but also scales gracefully when subjected to increased workloads. The field of algorithm research continually contributes new ideas that are then refined and optimized for real-world applications, providing programmers with a powerful toolkit to tackle problems of varying degrees of difficulty. Beyond the code itself, modern programming involves a robust ecosystem of tools and practices that facilitate development, testing, and maintenance. Integrated development environments, commonly known as IDEs, allow developers to write, debug, and refactor code more efficiently by offering real-time error checking, auto-completion, and integrated version control systems. These environments often come equipped with debuggers that enable programmers to examine their code execution line by line, helping them identify and resolve issues quickly. Coupled with automated testing frameworks, these tools ensure that any changes made to the codebase do not inadvertently break existing functionality. Continuous integration and continuous deployment, CI/CD, pipelines have become standard in professional software development, further streamlining the process by automatically building, testing, and deploying updates as soon as they are committed, which in turn leads to more stable, reliable software that can adapt dynamically to evolving requirements. Collaboration is another critical element in modern programming. With the complexity of contemporary software, projects are rarely the product of a single individual. Rather, they are the result of coordinated efforts among teams of developers, designers, and testers. Tools like Git provide a version control system that allows multiple contributors to work on the same project simultaneously, managing changes through branches and merges while maintaining a comprehensive history of modifications. Platforms such as GitHub, GitLab, and Bitbucket have further enhanced teamwork by offering features for issue tracking, code review, and documentation sharing. These collaborative tools foster an open exchange of ideas and feedback, ensuring that the final software product benefits from diverse perspectives and rigorous peer review. This environment of cooperation not only accelerates development but also promotes higher code quality and innovation. Security is an inseparable part of the software development process, and programmers must be vigilant to protect their applications from vulnerabilities that can lead to data breaches, unauthorized access, or system failures. Techniques such as secure coding practices, input validation, proper error handling, and regular updates and patches are essential to maintaining a robust security posture. Developers are increasingly incorporating security into every stage of the development lifecycle, a practice known as DevSecOps, which integrates security checks within CI/CD pipelines. This proactive approach to security helps ensure that applications are resilient against threats and that any potential exploits are identified and mitigated as early as possible. In today's interconnected world, where the consequences of cyberattacks can be catastrophic, embedding security into software from the outset is not just best practice, it is a necessity. Another transformative influence in the field of software and programming is the open source movement. Open source software is created collaboratively and made freely available to the public under licenses that permit modification and redistribution. This model has democratized software development, enabling anyone with programming skills to contribute to projects, learn from established codebases, and innovate without needing proprietary tools. Open source projects such as the Linux operating system, the Apache web server, and countless frameworks and libraries have become the backbone of modern computing infrastructures. They provide developers with reliable, peer-reviewed code that can be adapted and extended for various purposes, thereby accelerating innovation across the industry. The collaborative spirit of open-source development has not only expanded access to knowledge but has also paved the way for communities where ideas are shared openly and collective problem-solving flourishes. The impact of software and programming extends far beyond the realm of technical applications. It fundamentally shapes how we interact with the world. Everyday applications, from banking and healthcare to education and entertainment, are built on the foundation of robust software systems. As these systems become more integrated into daily life, the skills and innovations of programmers directly influence areas such as artificial intelligence, big data analytics, robotics, and the Internet of Things, IoT. The automation of routine tasks, the prediction of trends using machine learning, and the real-time management of complex networks are just a few examples of how software transforms industries, making operations more efficient, cost-effective, and customer-centric. In many ways, programming has empowered individuals and organizations to solve problems that were previously considered insurmountable, opening the door to advancements that continue to redefine the boundaries of what is possible. The future of software and programming promises even greater transformations as emerging technologies push the envelope of what can be achieved. Developments in quantum computing, for example, are poised to revolutionize the field by harnessing the principles of quantum mechanics to solve problems currently beyond the reach of classical computers. Although still in its infancy, quantum programming represents a new frontier that challenges conventional ideas about computation and information processing. Similarly, the increasing role of artificial intelligence in code generation and software maintenance suggests a future in which programs can be written, optimized, and debugged with minimal human intervention. These advances could lead to systems that are not only more efficient but also capable of learning and evolving over time, adapting to changing requirements and even foreseeing potential issues before they arise. In essence, software and programming are the driving forces behind the digital transformation reshaping every aspect of our lives. They encompass a blend of art, science, and engineering that empowers us to translate abstract ideas into practical tools and applications. Every line of code contributes to a larger ecosystem of innovation, where collaboration, continuous learning, and adaptability are key to unlocking new possibilities. Whether developing an application that streamlines business operations, designing an algorithm that interprets massive datasets, or creating a platform that connects people across the globe, the contributions of software and programming are both profound and far-reaching. As technology continues to advance at an unprecedented pace, the role of programmers and the importance of robust, secure, and efficient software will only grow, ensuring that this vibrant field remains central to the evolution of modern society. Ultimately, the discipline of programming is not merely about writing code. It is about articulating solutions to complex problems and continuously exploring new ways to harness the potential of technology. It demands a rigorous application of logic, creativity, and persistent curiosity that drives individuals to push the boundaries of innovation. In a world increasingly reliant on digital systems, software stands as the cornerstone of progress, enabling breakthroughs that improve lives, empower businesses, and extend the reach of human ingenuity. Through ongoing research, dedicated collaboration, and an unyielding pursuit of excellence, software and programming will continue to define the future of technology, providing the tools and frameworks necessary for transformational change in every corner of our society.